Okay, let's just try some true-false questions in terms of turning and centripetal force. Turning at constant velocity means that you are accelerating. So first of all, what is centripetal acceleration? Newton's second law is F equals ma, but when you go into a circle, you need to have what's called centripetal acceleration, and that's equal to the velocity squared over the radius. And what that means is that it depends on how quickly you're trying to turn, the speed here, to pull you into the centripetal force, but it depends on how quickly you're going, the velocity here, and then it's inversely proportional to the radius of the turn, if it's a tighter turn versus a looser turn, etc. So if you're going at a constant speed, but you're turning, are you accelerating? But turning, you're accelerating. The answer is true. Like, really? I don't get it. Well, here's a rule of thumb. If you can feel it in your gut, you're accelerating. So even though your speed stays constant, what's changing as you're turning? Your what? Your direction, okay? So it's kind of weird that even though you're driving off an exit ramp on a highway at a constant speed, as you turn, you will be accelerating because your direction changes. A center-seeking force is called centripetal. That's what? True, right? Centrifugal force is a fake one. Centrifugal force pushes you away from the center of the turn, okay? Centrifugal force is that fictitious force that you feel, but that's actually false because this is a fake force. It's fictitious. Fictitious. How do you spell that? There we go. It's a fictitious force. You feel like you're being pushed to the outside of the circle, but nothing really has to do that. Here's another example. You know your laundry machine? What does it do on the last cycle to get the clothes dry? It what? It spins like crazy, right? And what happens is the clothes fly out and stick to the walls there, right? And it looks like then there's this centrifugal force shoving the clothes against the walls of the washer rather. And then the little tiny holes let the water fly out in a straight line tangent to the circle. But all it is if your clothes are going at 20 miles an hour in a straight line, what do they naturally want to do? Keep going 20 miles an hour, right? So then the walls of the washing machine push the clothes into a circle, and then the water flies out in a straight line. You see that? It's a fictitious force. On an unbanked turn, you need friction to provide a centripetal force. Answer is true. You need to have grip on your tires to pull in the circle. So a lot of times to help a car, especially on race car track there, what do they do to the road there? On an exit ramps on a highway, they bank it, right, to help push your car into a turn. If you lose traction in a turn, your car will have inertia and skid straight. Is that true or false? It's true, right? If you want to go in a straight line, you naturally will continue to go a straight line, so you don't want to lose traction there, right? Next, you need 2 times more centripetal force in a short turn with half the radius. So if you want to take a turn that's twice as tight, if you look at the equation for centripetal force, right, it's just velocity squared over the radius. So if you have half the radius, you're going to need twice the force. That's true. Okay? But how about if you're going twice the speed? Is it going to be twice the force? It's velocity what? Squared, right? So that's false because you're going to actually supposed to need 4 times the force there. Okay? So in racing, those are 2 factors that we balance. Hence we come up with the ideal racing line.